are in, I got it. My main interests are in statistical and numerical aspects of subspace system identification and on the fault diagnosis, which relates to fault detection, localization, and quantification. And today's talk would broadly relate to the problem of the unmeasured nature of the excitation conditions, which would connect all the methods that we'll be discussing. So the fact that we don't measure the inputs, full set of inputs that act on the degrees of freedom of our mechanical systems cause several challenges in structural health monitoring. And those challenges relate to the fact that, for example, when there's a rotating machinery on board of the structures that we monitor, the inputs to the system are a combination of an ambient input and some periodic input, and the consequent outputs contain some information about the structural modes and the modes of the input. We identify both of those set of the modes, and sometimes they are difficult to separate, and the estimates of the system modes are at times not very accurate. The second problem is that the parameters that we obtain from data, they are afflicted with uncertainty, so variance and bias. And while trying to match the physical model, some features from the physical models with the equivalent data-driven features, this uncertainty poses some challenges, and which is amplified when we have sparse sensor configurations, and there are many model parameters that we try to update. The last challenge that we'll be discussing is connected to the fact that the covariance of the excitation, so statistical properties of the excitation, can change throughout the period that we monitor the structure. That induces some changes, for example, in statistical damage diagnosis test, because it affects our features. That produces false alarms that render the use of structural health monitoring systems impractical. So, and today we'll be discussing methods to alleviate some of those problems. So we'll talk about removing the influence of the periodic excitation from the outputs without really measuring the periodic excitation. We'll talk about quantifying the statistical uncertainty in subspace system identification, and also accounting for the uncertainty in damage diagnosis. So I will start with subspace-based harmonic removal. So the problem that we face here is that, as I mentioned earlier, that inputs are a combination of ambient load and periodic excitation. They act on a system, which we assume is linear time invariant, and they produce some outputs through the system filter. The outputs contain the information about the periodic modes and system modes, which we both estimate, for example, with subspace methods. The system modes are sometimes badly estimated because there can be some interaction between the periodic modes and the system modes. And at times we can try to filter the harmonic excitation, but when we apply classical filtering, that can deteriorate the parameters of the system modes like that. So in the method that we proposed in this work, we try to remove these periodic inputs with some geometrical projections of data. So first, the idea here was to describe a model measurements in a combined state-space model that depends both on structure and periodic modes. Focus on periodic modes, which are estimated by classical SSI. Then compute the realization of the periodic subsignal using the Kalman filter. Then we pose that problem in a classic input-output identification premise, where we project this realization of the periodic subsignal orthogonally onto the raw measurements, removing its influence from the raw data. And then we use classic SSI on the clean data without harmonics. So when we look at the equations, we describe our system in combined innovation state-space model in a modal basis. So after the similarity transform, the states are decoupled to system and periodic states, the same as the state matrix, which is diagonal and contains some system and periodic poles. Now the idea is to compute a realization of this periodic signal, so the periodic states and the corresponding periodic poles, using the Kalman filter. So here we simply introduce a selection matrix that selects the periodic Kalman filter states and computes the response of the system only towards those states. When we have that, we can project that periodic subsignal orthogonally onto their own measurements, which we then prove that it removes the influence of that signal on the measurements. And it's very similar to input-output system identification. So, and after the projection, we have clean data, which we can use for identification of model parameters. First, we validated this approach numerically. We made a Monte Carlo simulation of a simple CZ freedom chain system. We excited the system with an ambient load and injected a periodic load whose frequency was at very close to the third frequency of the chain. So this slide shows the estimates of the natural frequencies and damping ratios before and after harmonic removal. So one of the first things that we can notice is that the estimates of the modes of the system, which are those blue vertical lines, they are consistent, meaning that on average, they correspond to the true modes of the system. And we also estimate the periodic modes that have very small damping ratios. And so they're all at the unit circle. After the harmonic removal, we still get consistent estimates of the modal parameters, but we don't estimate the periodic modes which are removed. So this empirically shows that our method is consistent, and we also prove it in the paper. Now the question is, why do we bother removing the periodic excitation when in both cases we get the consistent estimates of modal parameters? And that can be shown on real applications. So here we consider a small laboratory experiment of an aluminum plate. We excited the plate with random tapping and injected a periodic input close to the first natural frequency of the plate at 370 Hz. This slide shows the stabilization diagrams of natural frequencies that together with power spectral densities of the output measurements. So figure on the top shows the stabilization diagram before harmonic removal and figure on the bottom after. So first thing we notice is that in both cases we estimate all modes of the system. In the first case, before harmonic removal, we also estimate the mode of the periodic input. When we zoom on the first mode, we can see that for model orders below 20, we estimate kind of a mix of system and periodic mode. And for higher model orders, the stabilization diagram splits, and we estimate the system and periodic mode. After the removal, the periodic signal is removed, and we estimate only system mode all the way to small model orders. And now the true benefit of removing this additional signal is when comparing the estimates of natural frequencies and damping ratios to some reference estimate obtained from the structure, here the plate, from the signal without the periodic excitation. So, and that is shown on this slide. So here we have comparison of the modal alignments of the natural frequencies and damping ratios before and after harmonic removal, and those alignments correspond to the first mode. So the reference estimate of the parameter is labeled as this black dashed line, and here we can see that before harmonic removal, the mean value of the alignment of the natural frequency and damping ratio is quite far away from that estimate, so we have either a bias or large variance. After the removal, the natural frequencies are quite well aligned, and the damping ratio is closer, the alignment of the damping ratio estimates is closer to the estimate, and we expect that with more data, it will get closer and closer. The second application is fatigue blade test, and in fact, that was our real motivation for developing this method. So here the goal is to obtain Modal parameters of the blade during the fatigue test and without stopping the blade. The big problem in this case is the strong periodic excitation that the blade is subjected to in order to induce fatigue load. So, and this, when looking at the power spectral densities of the output measurements from such a blade, one can see that we have very sharp peaks that correspond to the harmonics. And the first peak is at, I can show it on my screen. The first peak is at 0.25 Hertz that corresponds, almost coincides with the first node of the blade. And each subsequent peak corresponds to the harmonic of this fundamental excitation period. So as
what was the excitation harmonic?
Pardon?
In the fatigue test, you mean,
yes, the excitation. Usually, such test is done that there's some heavy rotating object at the end of the blade.
What was the natural frequency of that?
0.25 Hertz.
Oh.
So, and that corresponds to the first mode of the blade that is hidden somewhere here, which we don't see. So the blade is in a kind of resonance, and it moves in the shape of the first bending mode and accumulates fatigue. And in the meantime, it gets damaged. So usually the test needs to be stopped. The engineers need to inspect the blade. Then if they find cracks, the blade needs to be repaired. And then the test needs to be started again. So the idea was to schedule the periods of stopping the test, not by some experience, but by results from, for example, structural health monitoring. We can flag damage, or by deterioration of the Modal parameters that we can easily estimate from data. With such data that contain the strong periodic inputs, the estimation of Modal parameters is difficult because they are masked by the high energy of that input. So when we applied our framework to that problem, we could remove this forced periodic excitation, which resulted in clean signals. So here we can, after the removal, we can easily estimate Modal parameters and do the classic damage diagnosis without worrying about periodic excitation. So, and that was it. So now I'll start with uncertainty quantification. The uncertainty quantification that I'll be describing relates strongly to subspace identification. So the first question is, why do we focus on subspace methods? And there are several reasons for that. First and foremost, subspace methods are consistent. So their estimates from those methods are converging to the true parameters, which was shown in many good papers in the past. So that allows us to focus only on variance, errors, and consider biased and digital. Those methods are direct, which makes them computationally efficient because they usually don't involve any optimization. And what allows us to quantify, use the framework that I'll describe to quantify the uncertainty, is the fact that we can relate the estimates from subspace methods to data covariances. When we do that, we can propagate the covariance of data covariance, which can easily be estimated from sampling, onto each parameter in the chain of the system identification. So state matrix, observation matrix, the poles of the system, and then model parameters. In my thesis and postdoc afterwards, we spent a considerable amount of time in applying such propagation framework and developing it to some higher order propagation for modal phase collinearity, for Mach, and for the transfer function. So in this presentation, I will focus on the MPC and show the results of for Mach and transfer function. So MPC is a modal indicator that is a function of mode shape. This indicator is bounded between 0 and 1. For 1, it indicates that mode shapes are real valued and the damping of the system is proportional. When it is below 1, the mode shapes are complex valued, and damping is not proportional. So here I show two modes of a plate. The first mode is real valued, it's approximately real valued. And you can see that the components of that mode shape move in phase. And the second mode is complex valued, and the components of that mode shape move a bit out of phase, so the mode shape is kind of wobbly. The MPC of the first mode shape is around 1. The MPC of the second mode shape is below 1 at 0.95. And the problem that we are dealing here is distinguishing the threshold for the MPC that would yield us real valued modes or complex valued modes. So when MPC is, for example, at 0.99 or 97, what does it exactly mean? And to do that, we decided to analyze the asymptotic properties of the MPC. And the solution for that is the application of the first order perturbation theory. And we develop a second order perturbation theory to deal with that as well. Going back one step, before characterizing the distribution of the MPC estimates, we will discuss the distribution of the mode shapes that the MPC is based on. So mode shapes, when obtained from data and identified with subspace methods, are asymptotically Gaussian. That means that when we estimate mode shape many times from different data sets, the histogram of mode shape components should be Gaussian. And this allows us to approximate its distribution function. And this can be done with delta method, which, as mentioned earlier, propagates the covariance of data covariance onto the mode shape estimates. And this allows us to approximate the distribution of the mode shape components from one data set. So, and this distribution, as on the right part of the top figure, should correspond to the empirical Monte Carlo histogram of the mode shape estimates. So that means that delta method is very practical, because instead of evaluating mode shape many times and computing the properties of its distribution empirically from something, we can apply delta method and obtain equivalent properties from one data set. Going back to the MPC problem, knowing that mode shapes are asymptotically Gaussian, and here centered around some true value and with covariance matrix sigma, we can apply the delta method to characterize the distribution of the MPC. We do that by first making a first order Taylor expansion of the MPC estimate, which is the second equation in the second box, where we expand MPC around its true value, and we have a first order term that where J relates to first order derivative of MPC towards the mode shape. And this derivative can be obtained analytically easily. And the second term is the difference of the mode shape estimate and its true unknown value. So this first order Taylor expansion allows us to characterize the distribution of MPC as Gaussian with delta method. So we approximate the distribution of the MPC by Gaussian, and it's centered around, we write that it's centered around its true value, and with covariance matrix that relates to the covariance of the mode shapes and the first order sensitivity. So now, as we characterize the distribution of the MPC estimates, we can see how is the fit of one delta method based distribution to the empirical histograms of the MPC. So for that, we did some numerical Monte Carlo simulation of a 6-degree freedom chain system. We designed a damping matrix of that system to be non-proportional, such that fifth mode shape is complex value, and the corresponding MPC is below 1 at 0.9787. And the third mode shape of the system is real valued, and the corresponding MPC is sharp at 1. Then we make a Monte Carlo simulation, estimate mode shapes from different data sets 1,000 times, and then compute the corresponding MPCs. And that yields us to histograms that are presented on this slide. So histogram on the left is the histogram of the MPC corresponding to the complex valued mode shapes. There we can see that this histogram is, has a Gaussian shape, and the delta method based distribution obtained from one dataset fits this histogram well. The histogram on the right corresponds to the MPC of the asymptotically real valued mode shape. And here we can see that this histogram accumulates at 1, and its distribution is nowhere to be Gaussian. So that urges us to develop another framework to characterize its distribution. So we decided to look on further Taylor expansions, and we developed a second order Taylor expansion of MPC estimate, where we add a second order term, which is a quadratic form of mode shapes. So H is a Hessian, which is a second order derivative of the MPC towards the mode shape. Then we notice that when the mode shape is real valued and its MPC is at 1, then the Jacobian is equal to 0, which we can prove, and vice versa. That allows us to characterize the MPC estimate only with the second order term. So write the estimate of the MPC only in relation to the quadratic form of mode shapes. So now when we have that, we need to characterize the distribution of this expression Q, which is a quadratic form of mode shapes. So recalling that mode shapes are asymptotically Gaussian, there are some results in mathematical statistics that approximate the distribution of the quadratic form of a Gaussian variable with a chi-square distribution. So in my work, we prove that the quadratic form of mode shapes with Hessian in the middle can be approximated by scaled and shifted chi-square distribution. So in consequence, that we derive two approximation frameworks for the MPC estimates. One that allows us to characterize the distribution of the MPC estimates as Gaussian for complex valued mode shapes, and the second framework characterizing the distribution of the estimates of the MPC as chi-square distribution for real valued mode shapes. So when updating the histogram fits, we can see that the chi-square distribution that we derive from one dataset fits the MPC histograms quite well, and that allows us to define a decision framework where we decide whether a mode is complex valued or real valued just based on the MPC estimate and its uncertainty. We applied similar reasoning to MAC, and there our goal was to determine whether independent mode shape estimates are equal or different based on data. And as you imagine, that relates to the problem when we have MAC at, let's say, 0.95 or 0.97, what is really a threshold to decide that mode shapes are the same or equal. So we applied similar strategy to analyze the asymptotic properties of MAC, and derived the first and second order expansion of MAC to characterize its distribution. I skipped all the derivations because they are quite similar as for the ABC, just the derivatives are a bit more complex, and we'll focus on results. So here we have two histograms. The one on the left corresponds to MAC computed from statistically different mode-shaped estimates. There we can see that the distribution of those MAC estimates is close to Gaussian, and the true value of MAC is between 0.97 and 0.98, which is quite high, but still mode shapes are statistically different. And the first order delta method based theory allows us to approximate the distribution of the histogram, and the fit matches histogram quite well. You can see that we overestimate the variance of the distribution a bit, but that might be related to the data set that we chose to plot that fit, because we have 1,000 data sets, so we took one. When we look at the histogram of MAC estimates of statistically the same mode shapes, we can see that they accumulate at the border of the distribution, and the second order delta method based framework to characterize the distribution of that mode MAC fits well to the histogram. So that allows us to determine whether the mode shapes are statistically different or statistically the same. We applied this framework to track changes in mode shapes in S101 bridge benchmark. So S101 bridge is a bridge that was in Austria that was demolished, but before it was demolished, it was there was some long-term structural health monitoring campaign ongoing on that bridge. So we have multiple data set that corresponds to some healthy state of that bridge and some different damage states. So the idea, and on this slide we see several, and the three figures on the top of the slide, they show MAC obtained between some reference mode from the first data set and the mode shapes tracked in a data set corresponding to different states of the bridge. So we have some healthy data here, the damage data corresponding to very small damage, and then gradually increasing damage. So what we can take out from those three figures is that when we compute MAC between independent mode shape estimates that are obtained from healthy data, they are satisfying the confidence interval of the chi-square distribution that we use to approximate the MAC of equal mode shapes. However, when the damage starts, the MAC they start to be outside that confidence interval or the quantile of the distribution, which signifies that mode shape starts slowly to change. The MAC values, however, are still very high and still very close to 1, but we can still distinguish the small changes in the mode shape with that framework. Now, one very valid question that was asked by our reviewers is why you don't compare natural frequencies, because one can distinguish different modes just by looking at the frequencies. That's a very valid point. And here, to answer that question, we show how the natural frequencies, they change due to damage. So we can see that the natural frequencies of the first three modes in the healthy state, they are within the same confidence interval of some reference frequency obtained from the first data set. But when damage starts, they start to be outside that interval. And that is except the first damage case, when the damage is so small that the natural frequency it doesn't react to damage and stays within the uncertainty bounds of the reference natural frequency. And here our approximation framework from Mach distribution comes in handy, because we can distinguish the small changes in mode shapes by that framework, which is not distinguished by the just by looking at the natural frequencies. So that's the benefit of that development. One of the last slides and developments regarding the uncertain qualification is the characterization of the distribution of the transfer function. So here we computed characterized the distribution of the transfer function as a function of statistical properties of the state-space matrices ABCD. The challenge of this development, and this is only first order framework, however, the challenge of this development was to link the estimates of the input matrix and the feed-through matrix to the data covariance, since they are usually obtained from time series. But after doing so, we developed the first order perturbation theory that allows us to derive confidence intervals, for example, for the magnitude and the phase of the transfer function, which are shown here on those two figures. The application that we were aiming with such a development was the damage localization or damage diagnosis methods that utilize the transfer function that could be enhanced with some statistical evaluation about its properties, and in particular the dynamic damage locating vectors from Professor Bernard. So that concludes the uncertain quantification part, and I'll move to statistical damage diagnosis part. In this context, we also made several contributions. The first one was regarding developing a damage detection method that is robust to changes in the statistical properties of the noise. So there we develop a normalization scheme that allows us to normalize the data-driven features that we use for damage diagnosis, so they are not affected by the changes of the noise covariance, and which we can ensure won't produce false alarm in structural harmonic. About this, I have a few slides at the end, but in the following slides, I would like to focus on the second development, which is regarding accounting for the uncertainty of the target features in model updating in context of fault quantification. So for this development, it's quite similar to the work done here in the group. So we pose the problem of damage quantification as matching some features of data to features of the model, and we achieve that by monitoring the mean value of some residual between data and model. So first step is to design a residual, which we design to be Gaussian and designed to be a function of the estimates from data and some equivalent features from the model. Both data and model are parameterized by some parameter theta that fully parameterizes, we assume that it fully parameterizes the damage. The model, here the parametric state space model, also depends on theta, and it is a function of mass, damping, and stiffness of a mechanical system. So now to define whether the data and model match, we make two hypotheses. The null hypothesis, where we define that model parameterization matches, which is theta, matches the data parameterization, which is unknown. Then we design the residual function to be Gaussian with zero mean and some covariance matrix sigma, which is a sphere of uncertainty that encompasses the data difference between data and model. And we define alternative hypothesis where the model parameterization theta doesn't match the data. And in this case, the residual is also Gaussian, but it is its mean is shifted by some delta, and it also has covariance sigma. So our task now is to find the parameterization of the model that would match the data, and we do that by monitoring the mean value of that residual. So to take a statistical decision whether the mean value of that residual is 0 or non-zero, we do statistical hypothesis testing, and we utilize generalized likelihood iteration test. So the expression for the test is given here. The J in this case is a first order derivative of the residual that we use towards the system parameterization. The benefit of doing such hypothesis tests is that we know its approximate distribution under both hypotheses. So under null hypothesis, when data and model match, so what we aim for, the test follows a central chi-square distribution with degrees of freedom that relate to the rank of the Jacobian matrix that we can compute prior to trying to find model parameterization. And under alternative hypothesis, the distribution of the test also follows a t-square distribution, but now this distribution is non-central, so its mean value is a bit shifted. Knowing the distribution properties of the test under null hypothesis allows us to define a decision threshold, which would be a threshold until which we will try to match data and model. Any matching below this threshold would give us statistically equivalent results. So it doesn't, it is simply additional computational burden to do. So to match data and model, then we minimize the value of that GLR test with some evolutionary minimization strategy. On this slide, I show some results from the numerical application of this method. For that, we considered a simple B model parameterized with 95 parameters. Before doing the optimization, we reduced the parameter space with damage localization, where we define the clusters of parameters that react to damage, on which then we focus the optimization. This slide presents some earlier iteration of the work, where we didn't use the statistical hypothesis test for the objective function, but we used a simple difference of the natural frequencies and MAC together with their statistical distributions. So we used the information about the uncertainty of the features that we target to optimize data and model, first to shape the objective function that is shown on this slide. So here, those two figures, they show the slice of multi-dimensional objective function defined for two parameters. The function on the left corresponds to the objective function, which is not weighted with the uncertainty. So we can see that it's quite flat. And the function on the right corresponds to the objective function where we weight with the uncertainty of the natural frequencies and the quadratic map, where we can see that this function is whacked and steeper, which makes the optimization converge to the minimum faster. For the optimization, we use covariance matrix adaptation strategy, where we also define an uncertainty-based stopping criterion, so the optimization doesn't continue after we statistically match data and model. So on this slide, there are some results from the optimization. The figure on the left shows the value of the optimized parameters for the first iteration of the optimization and for the last. So there were around 30 iterations. So for the first iteration, one can see that the value of the parameters are quite spread around the parameter space. And the last iteration is the parameters are quite concentrated and hopefully around the true value of the parameter. Then we make a zoom only on the parameters that satisfy the stopping criterion, which is shown on the figure on the right, where we can see that the true value of the parameter is within the cloud of points that satisfies the stopping criterion, and the chosen solution from the algorithm that we developed is within those points. So by inducing the uncertainty-based stopping criterion, we could stop the optimization and alleviate the corresponding computational burden, and weight the objective function so the optimization strategy finds the minimum a bit faster. And that would be all, and I will conclude. So during my doctorate and postdoc, we were developing problems, some theory to solve some practical problems in structural health monitoring. We advanced the vibration-based structure monitoring by obtaining better estimates of system parameters during periodic excitation, assessment of the physical model properties by data estimates, and some methods for robust damage diagnosis that we haven't gone through here. Many of the algorithms were tested on large-scale structures, and most of them they were transferred to commercial software for structural health monitoring. And thank you.